Alright, so today what we're going to do a couple practice problems to get you guys ready and make sure you're understanding these buffer problems. So this is the first practice problem, and again you can pause me and you can do this problem and then listen to me going over this problem. Now in this problem, if you look at it, I am mixing hydrochloric acid with ammonia. What type of reaction is this? I'm mixing an acid with a base. So what I have here, I have an acid-base reaction. I'm adding an acid and base together. And remember, every time you have an acid-base reaction, what you have a single arrow. Is not equilibrium, right? Is not equilibrium because it's an acid-base reaction and it has to do with moles, right? It has to do with moles, or sometimes I do millimoles because it's a nicer number, and it has to do with limiting reagent. So every time you have an acid-base reaction, because one acid will react with one base, so you have a limiting reagent and you have a mole problem, not an equilibrium. It's a straight up reaction. This reaction will happen. There is no backward reaction. So I have hydrochloric acid plus ammonia in this reaction. I'm going to the next page so I have more room. So what's going on here? I have hydrochloric acid plus ammonia. I have an acid-base reaction, one arrow. The acid is going to lose a hydrogen. That doesn't change. And the base is going to get a hydrogen. So if ammonia gets a hydrogen, because ammonium, and then the HCl is going to lose the hydrogen. Okay. Now, again, this is an acid-base reaction. Every time we have an acid-base reaction, we don't do an ICE table. We do an, and I just did an ICE. We do an ICF. Is initial, change, final. Okay. Now again, we talked about this. We have to do moles here. Now I have the molarity of hydrochloric acid, which is 0.10 molar. I said if you have molarity is moles per liter, or molarity could be millimoles per ml. And I kind of like that in these problems because it gives me a nicer number. So I don't know the millimoles, but the volume of hydrochloric acid is 100 ml. Again, just look at the problem. So I can figure out the moles or the millimoles, which is 10 millimoles of HCl. I'm going to do the same thing for NaOH, 0.14 molarity. I can do moles per liter, or I can do millimoles per milliliter. It's the same thing. I have 50 ml of NaOH. So ammonia. What I end up getting is 7 millimoles of ammonia. So far so good. Okay. So then I'm going to come back here and I'm going to put in this mole value over here. So for hydrochloric acid, I have 10 millimoles to begin with, and for ammonia I have 7 millimoles, and none of this at the beginning. Okay. And then again minus X, and X. Now, remember this is an acid-base reaction. Every single one HCl reacts with one ammonia. One HCl reacts with one ammonia. I have 7 HCl, I have 10 HCl, I have 7 ammonia. So which one is a limiting reagent? So it's a 1-to-1 ratio, which means my limiting reagent is ammonia, right? Because I have 7 of this, I have 10 of this, 1 HCl reacts with 1 ammonia. So my X basically is 7 here. My X here is 7. So this would be minus 7, this would be minus 7, this would be plus 7. If I do that, I end up having none of the limiting reagent one. I end up having 3 of hydrochloric acid left, and I end up having 7 millimoles of ammonium left. Now, what do I end up with? This is what I end up with. What is left at the end is a strong acid, HCl, and a weak acid, ammonium. If you remember, we said when you have a strong acid and a weak acid, when you're trying to figure out the pH, you can almost ignore the weak acid, because strong acid has so much H plus that the few H plus that a weak acid has doesn't make much difference. It's kind of adding a drop into an ocean. So since I have a strong acid here, I can just figure out the pH based on my strong acid. Now the pH is minus log of H plus, of course. So I'm going to figure out the concentration of hydrochloric acid. So here the hydrochloric acid, I have 3 millimoles left, right? I have 3 millimoles left. The final volume is what? I added 100 ml plus 50 ml. So 100 plus 50 ml, 150 is my final volume. So I get 0.02 molar hydrochloric acid. And again, hydrochloric acid is a strong acid. Every single thing would break up. So I have 0.02 molar hydrochloric acid. That means I have 0.02 molar of H plus. Okay, so then minus log of 0.02 molar. What I end up getting is 1.70 is the pH. Now, like I mentioned before, what you could do is you could also figure out what's going on with the ammonium. Do an ice table. You have a Kb, you can figure out a Ka and figure out the hydronium concentration and then add it together. But we did a problem before. If you have a strong acid and a weak acid, you can just ignore the weak acid. Alright, so far so good. Now let's do the next practice problem. Let's do our next practice problem. Okay, so here's our next practice problem. Again, you can pause me and you can try to do this practice problem before you look at my work here. Now, if you look at this problem, you have hydrofluoric acid and you have sodium fluoride. Okay. Now, I have hydrofluoric acid, weak acid. Every time I see a weak acid, I go, weak acid, what I could do, I can do an equilibrium. For weak acid, you should do an equilibrium. Acid loses a hydrogen and the water, which is a base, gets a hydrogen. In this problem, what you have the weak acid and you have its conjugate. Every time you have a weak acid and you have a conjugate, what type of problem do you have? Hopefully you're yelling at me to the computer that it's a buffer problem. Okay. Now I didn't even need to read the question to figure this part out. Now in this question it says, what would be the change in the pH? Because it's a change in the pH, that means I also need to figure out the pH of the original solution and the pH after I add KOH and then subtract it, because it's a change in pH, so I need to figure out the pH of the original solution. Now this is my original solution, okay? This is my original solution. My original solution, what I have a buffer problem because I have a weak acid and I have this conjugate base. Now, if you have a buffer problem, you have two ways to do this. You can do an ice table if you like. But we said before, you can do an ice table, but ice table takes a long time. A better way to do an HH equation, and that is much faster. Okay, let's do an HH equation right here. Remember, pH is equal pKa plus log concentration of acid bottom, concentration of the base is on top. I can do that. Now, I don't have the pKa, but I give you the Ka. Remember, minus log of Ka gives you the pKa. So I give you the Ka, that will be minus log of 7.2 times 10 to the minus 4. What I end up getting, 3.14. That's the pKa. So far so good. Okay. Alright, so here I have the pKa, which is 3.14 plus log. What is my HF concentration? If you look at the problem, my hydrofluoric acid concentration is 0.25 molar. And my fluoride concentration, my conjugate base concentration is 0.45 molar. Okay, now this is pretty good. So now all I have to do is plug it in. If I plug it in, I get a 3.40 my pH. Now I want to do a little side note before I move on to the next part. Now, is this a good buffer or a bad buffer? Again, just because you're a buffer doesn't mean you're a good buffer. And I mentioned this briefly before, but I want to mention it again. To have the best buffer, you want a 1-to-1 ratio of the acid and base. So you want a 1-to-1 ratio of hydrofluoric acid to fluoride ion concentration. Is this a 1-to-1 ratio here? Not really. It's not a 1-to-1 ratio. This is 0.25, this is 0.45. Not the best, but still a buffer. So again, the best buffer is 1-to-1 ratio. And the reason that the best buffer is 1-to-1 ratio, because then this goes away and the pH ends up being equal pKa. So if this was a 1-to-1 ratio, this would go away, the pH will equal pKa. So that's the best buffer. So we already know this is not the best buffer, but it's not bad, it's still a buffer. Now, so we have this original solution. This is our original solution. Now, what are we doing to this original solution? What are we doing to this original solution? We are adding KOH. We add KOH. Now, what is KOH? KOH is a base. KOH is a base. Now, if you add this KOH with a base, let's check this out. Base would not even be attracted to the base. Base on base does nothing. But when you add KOH, KOH is going to go and be attracted to hydrofluoric acid. So base will not react with the base, but base will react with the acid. Okay? So what do we end up having? So the base will react with acid. If you add KOH, what it would do, it would react with the acid. What is my acid here? Hydrofluoric acid. So if it ends up reacting with the acid, what do I have right now? Now I have an acid-base reaction. If you have an acid-base reaction, remember we talked about, if you have an acid-base reaction, it's not an equilibrium, it's one arrow. Usually use moles or millimoles and think about the limiting reagent when you have an acid-base reaction. Again, I have an acid-base reaction, I have this solution going on, I add KOH, KOH is a base, KOH will not be attracted to F-, KOH will be attracted to hydrofluoric acid. So I have an acid-base reaction, so HF plus KOH, single arrow is not, now the acid is going to lose the hydrogen and the base is going to get the hydrogen. Now if you're wondering what really happens to the potassium, basically to be more correct, instead of writing F, I could write KF, right? That's what would happen. Basically, this one is going to lose the hydrogen, this one gets the hydrogen, and the potassium would counterbalance the F minus. So far, so good. Okay, so here's in my acid-base reaction is not equilibrium, so it's ICF and not ICE. Now, remember we talked about, if you have an acid-base reaction, you want moles. Now, in this problem, I kind of made it easy for you. I said we have 0.25 molar hydrofluoric and 0.45 molar sodium fluoride in 1 liter solution. Because it's a 1 liter solution, okay? Let's go back here for a second. Because it's a 1 liter solution, the molarity will be the same as moles. The molarity will be the same as moles. Okay, so that means I have 0.25 moles of KF. And then for fluoride, I have 0.25 moles of fluoride ion in this solution. That's what I have in this solution. And I added KOH. How much KOH did I add? I added 0.20 molar KOH. I don't know how many moles I added, but I added, what did I say in this solution? I added 300 ml, so 0.300 liter, okay? So 0.300 liter. Okay, again, nothing that you've never seen before. This is just figuring out the moles, because what do I need? I need moles. I need moles to do an acid-base reaction. Okay, so 0.02 times 0.3, what I end up getting for the moles of potassium hydroxide. Okay, so we get, what we end up getting is 0.006 moles of KOH. So what I have here is 0.006 moles of KOH. All right, it's again acid base, you have to do moles. Now that I have moles, again, one HF will react with one KOH to form F minus. Now remember, this is minus X, this is minus X, this is plus X. But what is my limiting reagent? This is a little obvious. This is my limiting reagent, the KOH. I don't have much of it. I will run out of KOH before I run out of hydrofluoric acid. So that means my X is minus 0.006, minus 0.006, and plus 0.006. Now if I do that, I end up none of the KOH. I end up with none of the KOH, okay? End up with none of the KOH. And then over here, I end up with 0.256 moles of F minus. And over here, I end up with 0.244 moles of hydrofluoric acid. Okay, what do I end up with? What is left at the end? What is left at the end is a buffer solution, isn't it? What I end up having at the end, I'm going to have a weak acid and a conjugate base. So weak acid as conjugate base, I end up having a buffer solution. So I can use the HH equation again to figure out the pH of this solution. So far so good. Okay. Now again, pH is equal to pKa plus log. I have my HF concentration here and my F minus concentration on top. Now remember, when you have the HH equation, what you need is molarity. It's not going to matter because the volume technically cancels out, but I want us to do it the right way. So what you need is molarity. What you need is molarity, because here what we have, these are moles. We use moles. I want to convert it back to molarity, and I want to do that because we want it to be the correct way. So for F minus, what I had 0.256 moles. Now, what is the entire volume now? Remember, it was a 1 liter solution. I add 300 milliliters to it. So the entire solution is what? The entire solution will be 1.3 liters, okay? It will be 1.3 liters. So what I end up getting is 0.197 molar. Now hydrofluoric acid, I have 0.244 moles left. 1.3 liter solution. Again, it's a final volume. When you add everything together, what I end up getting is 0.187 molar. So far so good. Okay, so I have those two molarity. And do I have the pKa? Yeah, I have the pKa from before. The pKa was 3.14. So the pKa is 3.14. And now if you add everything together, what you're going to end up for the pH is going to end up being 3.16. That's the pH that you're going to get. Did the pH change much? You know, not too much. Went from 3.40 to 3.16. It changed a little bit, and again, it changed because we did not have the best buffer solution. The best buffer is when you have a 1-to-1 ratio between the weak acid and its conjugate. We didn't have a 1-to-1 ratio. Not the best buffer, but it's still not bad. You added a strong base, and the pH still in the 3. All right, so you had 2 practice problems to practice from. Nice job.